So this is problem 6. So first A, we estimate the value of time constant tau and the steady state current at each voltage clamp. So that's pretty easy. So the easiest thing is the steady state current, like at each voltage. So we see that, okay, so at negative 20 volt, there's like maybe like 0.6 milliamp per square centimeter, and this is like maybe 0.3, and this is maybe like 0.1. At negative 60 and at negative 80, it is 0, and at negative 100, it is maybe like negative 0.1 amp per square centimeter. So there's that. And then for tau is the easiest. How we get it is that, as shown here, at one time constant, it is so it is the time at which the value reaches 63% of the steady state value. So this is like steady state value is 0.6. So 0.63 times 0.6 is like 6 times 6 is 36. So roughly like 3.6. So around here, somewhere close to 0.4, and it takes about like 1 second to reach the like 0.36. So time constant here is 1. And in similar fashion, so the time steady state is like maybe like 0.3. So to reach the 63% of this, which is like, 2/3 basically, and it is then 0.2. And to reach 0.2, it takes like 2 seconds or so. Well, actually, maybe not. So in this one, it says like 1.5. So 1.5 second is the time constant, and so on and so forth. And then what is the value of EY, which is the equilibrium potential of Y. So Y is like this is like the probability or the percentage of the ion channels that is open. And so if 50% of it is open, then it makes sense for the 50% to be closed. If it's 70, then this would be 30%. Makes sense. So this is basically like a steady state value of the equilibrium potential. So what that means is that if it's steady state, then it always has to be the current or the number of ions that is moving through the membrane has to be 0. If not, the steady state cannot be sustained. So it is obviously negative 80. And the last one, the plot is y infinity, y steady state, alpha y, alpha beta y as a function of v. So how we solve it is through this. So I'm just gonna use negative 40 as an example and like try it. So with this one, negative 40, we know the current, the steady state current is like maybe 0.3, right? Which is shown here. And then time constant is like, sure, maybe like 1.5 because the 63%, so at 0.2, the time is 1.5, so great. So we have this basic value over here, and we need to figure out the y infinity, or the steady state probability of or the percentage of the ion channels that is like open. And we have these equations here, just to memorize this. We could derive it by rearranging it and I think integrating it, but it's a lot easier to just memorize this or put in your note. So once you have that, then we can rearrange, and so we have these equations, and we have like two unknowns, alpha and beta, so we can like solve it. So how I did it was, so that's the equation, and you can rearrange it for alpha, which is this just goes here, and that's it. And for time constant tau, it's 1 over alpha plus beta, and then so that means alpha plus beta is 1 over tau. And another important equation is this, so we need to get this to get going, and I infinity, which we know from 0.3, which is the current, the steady state current at a certain voltage, and this is conductance, which should be given to us from the questions, and then V is the voltage of our interest, I guess. So VC, which is negative 40, because that's what we're using here, and then EY is the steady state, like the So potential, so it's like negative 80 when the I is like 0. So negative 80. So if you put all these numbers in, crunch the number in, so 0.3 over 10 times negative 40 plus 80, basically. And if you do that, you will get 2.5 times 10 to the negative 4. Be careful for the numbers, like the square, because of the unit. You have to do unit analysis. Actually, no, that's not what you get. That's a wrong one that I just made a mistake. So if you put all this unit in, so don't make mistakes like this. And then it works out to be 0.75. So what you have to do for this one, at least in this particular example, just do all with the basic numbers, and then just multiply by 1,000, and you'll get this number. Because there's milli, so it kind of cancels out, but this is still a millivolt, so you have to multiply by 1,000 to mitigate that. But anyway, so you get 0.75, and by that point, you're kind of already done. It's really easy from here, because you know this number, and you know this tau. So tau, we already know that here is 1.5. So tau is just alpha 1 over 1.5, which is 0.67. You already have it here, and then you just figured out this as well. So 0.75 times 0.67, and then you get 0.5, and then beta. Well, once you know alpha, which is 0.5, you can just put it in here. Okay, so 0.67 minus beta 0.5 would be 0.17. So we have this number, and that's where all these numbers comes from. And you just repeat it, and then you can draw this nice graph or plot of voltage, and then there's alpha, and then it seems so negative 20. So as the number goes down, or the voltage decreases, alpha is highest at 1. I mean at negative 20, and then it goes down exponentially, it seems. So for alpha, you will have something like that, and for beta, it'll be the other way, because beta is the opposite of alpha, which is so beta is opening to closing, and then alpha is closing to opening. So it'll be like that. Oh, and plot y infinity. So once you do all those, we can see that as the voltage decreases, so does the y infinity. It seems like it's decreasing exponentially too. But so it's kind of similar to this. But yeah.